Hi everyone. In this video, let's think about some simple equations in three-dimensional space. But we are going to begin in 2D. And so suppose in two-dimensional space, we are going to graph the equation that's given by y equals 1. And I know you know what this graph looks like, but I am gonna draw this anyway. So here is x and y axis. Now in two-dimensional space, since we only have x and y variables, we need to just consider set of all points on this xy plane where the y coordinate is fixed at 1. So as you know, we go up to y equals 1, and since x can be anything, we end up getting this horizontal line where the y value is exactly 1 while the x can be anything. So let's think about what's going to happen if we try to graph the same equation in three-dimensional space. Well, you know that in three-dimensional space, we are dealing with three variables. So here is the y-axis, x-axis comes out this way, and here's the positive z. And if you think that equation y equals 1, the same exact equation, is going to give us a line in this case, then you do need to stop and think about this a little bit. So if I were to go where y value is exactly 1, and if you think that this is going to just give us a line, then you would have to extend this point indefinitely in one direction. But if the equation is y equals 1, then that means that x and z value can be anything. So in three-dimensional space, if you are fixing only one variable, then you need to extend that point that you have into both x and z direction. So do you see what we're going to get for the graph? I don't know you actually have your conclusion, but when you extend this into both x and z direction, what you are going to get is not a line, but we are going to get a plane. So instead of trying to draw this, I am going to give you a graph for that. So here is the plane y equals 1. And you can actually see that this thing is going through along the y-axis where x equals 1 and extending forever both in x and z direction. So what this example is telling us is that when you are given an equation in three-dimensional space that is like x equals a constant, y equals a constant, or z equals some fixed value, a constant, then those equations define a plane. So using this idea, let's think about the following. We saw these pictures of coordinate planes earlier, but let's try to come up with the equation of each of these coordinate planes. So this plane, xy plane, that's containing x and the y-axis, these are the points where x and y can be anything, while the z value has to be exactly 0. So the equation for this plane is going to be z equal to 0. Now this green one, this is the xz plane containing the x-axis and the z-axis. What's being fixed here is the y value. So the equation is going to be y equal to 0. Now lastly, this brown plane, this is the yz plane containing the y-axis and the z-axis. The value that is being fixed along this plane is going to be the x value, which is fixed at x equal to 0. So let's try this example. This is asking us to find an equation of the plane that is containing the point 2, negative 3, 5, but parallel to the xz plane. So let's try to visualize this a little bit. So here is the z-axis. Say that this is the y-axis and the x-axis, like so. And the x value is 2, while the y value of the point is negative 3, and z is 5. So let's say that this is where z is 5. So the point that we are considering would be something like that. Okay, so the plane that we're considering has to be containing this point 2, negative 3, 5, but needs to be parallel to the xz plane. So it's the plane that is containing the x-axis and the z-axis. So if this is parallel to that, then the x and z value is going to have to be anything, except for the fact that the y value needs to be fixed at exactly at negative 3. So the equation of such plane is going to be given by y equals negative 3. So let's end this video by looking at a little bit more interesting examples. And these equations are not as simple as the ones that we looked at before, but we can try to do exactly the same thing. So for example, the first one, y equals x. Since this equation only involves y and x, we can try to visualize what this looks like on the xy plane. And then, since z variable is missing from the equation, what that tells us is that whatever we get along the xy plane, we get to extend that into the z direction, straight up and down, right? So this is what we get. So here is the three-dimensional coordinate system, and we can draw the line y equals x on the xy plane. So that would look something like this. So please pretend that this is the line on the xy plane that's given by y equals x and the xy plane. But this equation is supposed to be considered three-dimensional equations. So what we need to do then is that every single point on the line needs to extend straight up and down into the z direction. So even though I won't be able to draw this very well, this is going to be what the graph might look like. So please understand that this is a plane going through the origin that you get by extending the line y equals x in z direction indefinitely. So let's apply the same idea to this equation y equals x squared. So again, it is going to be a bit more difficult to draw this, but we can try to draw y equals x squared, which is a parabola, right, on the xy plane. So this would look something like maybe something like that on the xy plane. So just like before, since this equation is missing the z variable, what we need to think about is that the graph of this equation is going to be obtained by extending that curve in z direction indefinitely. So in this case, the graph might look something like this. So over here, you're gonna have the same copy of the parabola in the z direction. And this vertex also comes straight down. And of course, this thing is supposed to be extending forever in the z direction, but maybe the surface might look something. Let me just erase this part here. Something like that. So now what about this last example? This is an equation in x and z, but we can still do the same thing. We can try to look at what this thing gives us in the xz plane. And since the y variable is missing from the equation, whatever we get on the xz plane, we are going to extend indefinitely now in the y direction. Okay, so what is this object given by x squared plus z squared equals 4? Well, if you just replace z with y, you know that this is an equation of a circle centered at the origin with radius 2. So, yeah, I think we can draw that, even though it's not as simple as drawing it in the two-dimensional space. But let's say that here is the cross-section of the circle in the xz plane. Sorry about my picture there. But if this is the circle of radius 2, then I guess this z coordinate here should be 2, and the x right here should be 2 also. But now what we need to do is to extend this circle indefinitely in the y direction. So you are going to get something like so. So you can see that this is a circular cylinder, right? Now, by the way, though, the last example is also considered a cylinder. Anytime you have equation in three-dimensional space, and when one of the variable is missing, that is going to produce what's called a cylinder. As opposed to the third equation is giving us the circular cylinder. The last example is considered a parabolic cylinder since the cross section is a parabola. So anyway, I hope that these examples give you some ideas as to how to visualize and sketch, or at least attempt to sketch, some simple equations in three-dimensional space.